What if I told you that for the first time in history, we might have found a real chemical clue for life beyond Earth? 120 light-years from here, the James Webb Space Telescope detected a molecule that sent a jolt through the scientific world. On our planet, is pretty much only made by living things. You've probably seen the headlines, screaming about a near certainty of life on a distant world named K2-18b. This is the story of that planet and a discovery that has everyone asking that one big question: are we alone? But it's also a story about how science really works, because behind those sensational headlines, there's a more complex and, honestly, a more interesting truth. So, let's break down what the Webb Telescope actually found, separate the facts from the hype, and figure out what this all really means for the search for our place in the cosmos. The planet, the telescope, and the headline. To really get what's going on here, we need to meet the key players. Our story starts 124 light-years away, in the constellation Leo. There, a small, cool red dwarf star called K2-18 is orbited by a truly weird world, K2-18b. This isn't an Earth, it's a monster of a planet, about 8.6 times the mass of Earth and 2.6 times as wide. That puts it in a category we don't have in our solar system, a sub-Neptune, or, more excitingly, a Hycean world. The term Hycean, coined by researchers at the University of Cambridge, describes a hypothetical planet covered in a deep, global ocean of liquid water, all under a thick, hydrogen-rich atmosphere. And here's the kicker. K2-18b orbits in its star's habitable zone, the Goldilocks zone, where it's not too hot, not too cold, but just right for liquid water to exist. For years, K2-18b has been a top target for astronomers. The Hubble telescope gave us a hint of water vapor in its atmosphere, but it took the insane power of the James Webb Space Telescope to really pull back the curtain. An international team, also led by Professor Madhusudan from Cambridge, used Webb to stare at K2-18b as it passed in front of its star. This trick is called transit spectroscopy. Imagine trying to figure out what a bug's wings are made of by analyzing the streetlight filtering through them. It's like that. As the starlight filtered through K2-18b's atmosphere, different gases absorbed specific colors of light, leaving behind a chemical fingerprint that Webb could read. In 2023, the results came in, and they were huge. The first ever detection of carbon-based molecules, methane and carbon dioxide, in the air of a habitable zone. The presence of these molecules, plus a curious lack of ammonia, strongly supported the idea that K2-18b could be a Hycean world with a massive liquid water ocean. But hidden in that same data was something else, a signal so faint it was barely a whisper, a molecule that would soon be making headlines around the globe. The source of the hype, that tiny whisper in the data, pointed to a molecule called dimethyl sulfide. If you're not a chemist, that name probably means nothing. But if you're an astrobiologist, someone searching for life in the universe, that name is electric. Here on Earth, DMs is almost exclusively linked to life. If you've ever been to the beach and smelled that distinct, slightly funky sea breeze, you've smelled D. It's produced by tiny marine life, like for decades, scientists have theorized that DMs could be a powerful biosignature, a chemical signpost of life. So, when the first batch of JWST data showed a possible hint of DMs on K2-18b, it was, as the lead researcher Madhusudan put it, a real shock. It was an exciting clue, but the evidence was incredibly weak. It didn't meet the level of statistical significance needed for scientists to confidently say, "We found it." The signal was there, but it was faint, tentative, and could easily be a blip in the data. Despite the weakness of the signal, the mere possibility was enough to spark immense excitement, and, as we'll see, a whole lot of hype. The scientific team knew they had something potentially groundbreaking, but they also knew they needed much more proof before they could make any definitive claims. Deconstructing 99.7% probability. So where did all those 99.7% probability of life headlines come from? This is where we have to slam the brakes and separate the science from the clickbait. That 99.7% number doesn't refer to the odds of life on K2-18 billion. Not even close. It refers to a statistical confidence level known as 3 sigma. Think of sigma as a quality score for a scientific signal. A 3 sigma result means there is a 99.7% chance the signal is real and not just a random fluke in the data. That sounds pretty solid. But in high-stakes science, it's just considered interesting. For a formal discovery, scientists demand a 5 sigma result, which means there's a 99.99994% chance the signal is real. But here is the most important part. The hint of DMs on K2-18b didn't actually reach that 3 sigma level. the signal is still too weak and uncertain. So, while a 3 sigma detection of a biosignature would be a landmark moment, we aren't even there yet. This is how science is supposed to work. Bold claims demand extraordinary evidence. Since the data was released, other teams of astronomers have double-checked the work. Some have argued the data is just too noisy where the DMS signal should be, suggesting there's no detection at all. Another group even proposed that the faint signal could be explained by a much more common molecule, ethane, which has nothing to do with life. This back and forth isn't a failure. It's the scientific community rigorously testing a big claim before accepting it, building the case for a habitable world that confirmed science, while everyone is arguing about that faint hinted. It's easy to miss the discoveries about K2-18b that we know are real, and they are still revolutionary. The solid, undisputed detection of both methane and carbon dioxide in its atmosphere is a huge deal. These carbon-bearing molecules are the basic building blocks for life as we know it. Finding them in the atmosphere of a planet in the habitable zone is a massive step forward in our search for other worlds that could support life. What really makes this exciting is not just what Webb found, but also what it didn't find. The data showed a distinct lack of ammonia. Now, basic chemistry predicts that, in a hydrogen-heavy atmosphere like this one, ammonia should be everywhere. So where is it? Well, if the planet is covered by a giant liquid water ocean, the ammonia would easily dissolve into the water, hiding it from Webb's view. So, the combination of finding methane and CO2, while not finding ammonia, provides powerful, consistent evidence for the Hycean world theory. It strongly suggests K2-18b isn't just a gas ball, but a true water world with a planet-spanning ocean, and that alone is incredible. We now have tangible evidence for a whole new class of potentially habitable planet, and like anything in our own solar system, scientific caveats and alternative explanations. But science is all about asking what if, and K2-18b has a ton of them. The whole case for it being a habitable water world is unto the only way to interpret the data. Some scientists think K2-18 billion could be a gas dwarf, or a min with no solid or liquid surface at all. In that case, the pressures and temperatures deep in its atmosphere would be way too extreme for life. Even if there is an ocean, the planet is so large that the pressure at the seafloor would be crushing. And it's possible the ocean is actually boiling hot, not exactly a friendly place for a swim. And then there's the DMS molecule itself. Let's say, hypothetically, we confirm it's there with a 5 sigma discovery. Does that automatically mean life on Earth? Yes. But K2-18b is not Earth. Its hydrogen-rich atmosphere is a completely different chemical playground. Some scientists have pointed out that unknown non-living or abiotic processes might be able to create DMs in that kind of environment. Lab experiments have shown you can sometimes create DMs without life by zapping simulated exoplanet atmospheres with UV light. We have to be careful not to let our Earth-based assumptions blind us. There could be unknowns, geological or chemical processes that just don't happen here. This healthy skepticism is exactly why we can trust the process. Scientists want to be sure that when the day comes to announce the discovery of life, the evidence is absolutely rock solid. The story of K2-18b is a perfect example of science in real. It's a detective story where new clues and new debates unfold with every single observation. This journey is just getting started. To stay on top of every new chapter in this incredible story, and to keep exploring the biggest questions in the universe, make sure you subscribe and hit that notification bell. You won't want to miss what comes next. What's next? So, where do we go from here? The path forward is pretty clear. We need more data, a lot more data. That tantalizing hint has made K2-18b one of the most interesting targets in the night sky, and astronomers are lining up to point Webb back in its direction for a much longer, harder look. The research team figures that with enough follow-up observation time, they could finally settle the debate. More data could either solidify the DMS signal and reveal it clearly, or show once and for all that it was just a ghost in the machine. These future observations are critical. Beyond just DMS, scientists want to paint a more complete picture of the planet's atmosphere and climate. They allow search for other molecules that could help them choose between the water world and gas dwarf models. The more complete our chemical inventory of K2-18b is, the better we can judge its potential to host life. This whole thing highlights a huge shift in astronomy. Thanks to Webb, we've entered a new era. We're not just counting planets anymore. We're getting to know them. We're analyzing their air, debating their climates, and hunting for the chemical building blocks of life. K2-18b might be the first big test case, but it won't be the last. Each new world Webb studies adds another piece to the giant puzzle of our place in the universe. In the end, The real story of K2-18b is way more interesting than the sensational headlines. No, the James Webb Space Telescope did not find proof of life with 99.7% certainty. What it found is a strange, fascinating world that defies easy labels. A potential ocean planet, 124 light-years away, that is now the focus of intense scientific debate. It has given us the best evidence yet for a habitable Hycean world, a planet with carbon and strong hints of a global ocean. And it's given us a tentative, hotly debated, but undeniably exciting clue of a molecule that, on our planet, is a sign of life. The final truth about K2-18b is still out there, waiting for the next round of data to bring it into focus. But the search itself has already given us something profound. It has shown us that we finally have the technology to sniff the atmospheres of distant worlds for the chemical echoes of life. We are taking the first real, concrete steps to answering one of the oldest questions we've ever asked. Are we alone? Whether the answer comes from the skies of K2-18b or a world we haven't even found yet. One thing is for sure, the search has just begun.